Computational thinking in physics is the disciplined process of structured problem-solving. It takes unstructured data and raw inputs and transforms them into structured computational models by applying a logical framework. This process gives a sharper skeleton to the instinct for models and rules. There is a paradigm shift from programming to computational thinking. Programming focuses on syntax, compiling code, and instructing a machine. Computational thinking involves formulating the exact problem, systematic reasoning, simplification, and instructing oneself. Programming is a tool. Computational thinking is the deeper habit of mind behind it. The anatomy of a solution involves a framework that prevents the mind from being overwhelmed by complexity. This framework moves from the problem through decomposition, pattern recognition, abstraction, algorithmic thinking, representation, and finally, evaluation and debugging. Move 1 is decomposition, breaking a large problem into smaller pieces, such as analyzing the forces and conditions acting on a satellite. Move 2 is pattern recognition, looking for similarities. Physics loves structural echoes, like the mathematical similarities between a pendulum and predator-prey dynamics. Move 3 is abstraction, keeping what matters and ignoring what does not. This is disciplined, selective attention. Move 4 is algorithmic thinking, describing a solution as a precise sequence of steps, a human algorithm. This includes defining quantities, choosing coordinates, writing equations, applying boundaries, solving, and checking units. Move 5 is representation. A good representation, whether a graph, vector diagram, equation, or state variable matrix, can make the answer almost fall out by itself. Move 6 is evaluation and debugging. Error is normal, and debugging is an underrated intellectual virtue, focusing on checks like units, physical sense, extreme limits, known cases, and simulation convergence. Computational thinking has a hybrid lineage, drawing from mathematics for formal reasoning, logic for structured deduction, engineering for procedural methods, computer science for algorithms and automation, and scientific practice for model building and validation. Computational thinking, or CT, arrives because reality refuses to be simple. When pure intuition struggles against complexity, structured procedures stabilize the mind. The educational staircase moves from organizing messy info to translating words to equations, simulating systems, and distinguishing model from reality. Part 1 of the underlying philosophy states that the world can be modeled using structures, rules, and states. Complexity can be managed through decomposition and refinement. Abstraction is power, meaning deep, shared structures matter more than surface appearances. Part 2 of the underlying philosophy focuses on precision, which avoids verbal fog and requires explicit assumptions. Process is greater than the answer. Validity and repeatability are paramount. Finally, failure is informative, and debugging is philosophical humility, revealing hidden complexity. The principles matrix organizes computational thinking. Framing the problem involves clarity, modularity, and abstraction. Designing the solution uses generalization, algorithmic precision, and efficiency. Execution and review rely on iteration, verification, and automation. The ultimate point of computational thinking is not to worship computers. The goal is to free the mind for higher-level reasoning and intellectual pursuits. Welcome to the Blueprint of Nature, a visual manifesto for physics educators and problem solvers. This video explores computational thinking as the method architecture of physics. Computational thinking is not simply using a programming language or calculator. A student can write code without computational thinking, just as someone can push piano keys without understanding music. Code is most valuable when a problem is too complex for hand calculation. Computational thinking aligns with physics through 5 core areas: abstraction, models, multi-step algorithms, complexity, and validation. This alignment bridges the theoretical and the practical application of physics. Physics is not about collecting formulas. It is a disciplined attempt to understand nature. We contrast the formula collector mindset with the computational thinker mindset, especially when faced with unfamiliar or complex problems. The cognitive engine offers a 9-step architecture for problem solving, organized into setup, formulation, and execution and review. These steps provide a structured approach from defining the problem to generalizing the solution. Let's apply this framework to projectile motion. Steps 1 and 2 involve defining constants and making abstractions. Steps 3 and 4 involve decomposing the problem into horizontal and vertical components. Steps 5 through 7 involve solving and executing the calculation. Finally, step 8 involves verifying the solution by checking limits and units. The formula for range is just the final fossil. The whole workflow, from foundational assumptions to systematic execution, is computational thinking. Computational thinking acts as a universal engine across all domains of physics. The core mechanisms, such as decomposition and abstraction, apply consistently from Newtonian mechanics to quantum mechanics. In modern physics, when no exact analytical solution exists, computational thinking is essential. For planetary motion with drag, the computational path involves defining state variables, discretizing time, and updating iteratively. Physics gives us the content, the map of nature, the theories and models. Computational thinking provides the navigation machinery, the method architecture for formulating, organizing, and executing reasoning. The ultimate goal is to become a thinker who can approach new, complex problems without panic, even when a ready-made formula is unavailable. Computational thinking provides this essential structure.